Hello and welcome to another live stream from Portland State University's Learning Center. My name is Travis and I will be helping you through this today. Today we're going to talk about the types of different reactions there are. We're going to balance some chemical equations some more. We're going to work on the percent yield and other theoretical yield equations as well. So just to start things off, I like to post a few links that are useful. This is links to the Learning Center's webpage as well as their Facebook and Instagram. So if you aren't following them yet on Facebook or Instagram, definitely follow them. I'm also going to post a link to a YouTube channel that contains video links of everything that I've been recording for the last few weeks. So if you ever want to catch up for an exam or just review in general, if there's a concept you're missing, definitely check in there. You can also always schedule a tutor with our chemistry tutor, Amir, through the Penji app. Just go to web.penji.com and you should be able to sign in there with your Portland State information and get access to tutoring through there. It's a free of charge, and Amir is great, and I think he's available most days of the week too. You can also stop into my drop-in tutoring, which I'm going to be having after this Saturday live stream. So right after the live stream, jump into the Penji app, go to the drop-in tutoring, and you should be able to find me there. All right, and let's get started here. The first problem we have today is number 6 from the end of chapter problems and OpenStax. And this one says, write a balanced equation describing each of the following chemical reactions. So the first one is a solid potassium chlorate, KClO3, decomposes to form solid potassium chloride and diatomic oxygen gas. So it's a hard thing to kind of read it in words and then write it down into a formula. So that's what this is really trying to get you to recognize. So to start out, that potassium chloride, they say, is KClO3, and it's a solid. So we want to write the little S next to it there. And it's going to decompose, which means I put that little arrow. That's the reaction happening to form solid potassium chloride. That's KCl, solid, plus diatomic oxygen gas. So diatomic means there's 2 atoms in there. It's going to be O2 oxygen gas. Now our job, now that we've turned those words into an equation, is to balance it. So to balance it, we want to make sure there's the same number of atoms for each type on both sides of the equation. We're not losing any mass in here. None of it's turning into energy or anything weird like that. This isn't physics, just chemistry. So to start out with, I like to look at the most complicated one on the product side. That's going to be your KCl, because O2 is pretty easy to balance because there's only one there. We just have to make sure it kind of works for everything. So looking at the left side of the equation, the reaction side, we see there's 1 potassium and 1 chlorine. Same here, 1 potassium, 1 chlorine. So we're balanced for that already. Looking at the oxygen, we have 2 oxygens. Oops, I'm erasing. 2 oxygens and 3 oxygens. So there we have we're misbalanced. So we need to do something to this equation to balance it. So in this case, we have 2 and 3. So what we need to do is find the least common multiple between those, right? Which is going to be 6. So to get to the 6, we have to do 2 on the left side and then 3 on the right side. So by having 2 KClO3, there's just 6 oxygens on the left, and by having 3 O2, we have 6 oxygens on the right. But now we've misbalanced our potassium chloride, because now we have 2 potassiums, 1 potassium, 2 chlorides, 1 chloride. The easy fix to this, put a 2 in front of there. Now we're balanced. All of the atoms have the same on both sides. Looking at part B, solid aluminum metal, so that's Al, solid, reacts with solid diatomic iodine. So that's I2, diatomic iodine, solid, to form Al2I6. So we only have one product on the right-hand side of the equation. That's Al2O6. So aluminum diiodide, or hexaiodide, is going to have 6 of those iodides on there and 2 of the aluminum. So this is pretty easy. We just need to make sure we have 2 and 3. Because there's 2 aluminums on the right side, so we have to make it 2 aluminums on the left side. And since there's 6 iodides on there, we need to make sure we put a 3 in front of that, so 3 times 2 is equal to 6. Part C, when a solid sodium chloride, so that's sodium chloride, solid, is added to aqueous sulfuric acid. So it's added to sulfuric acid, H2SO4, I believe. Is that right? Yeah, aqueous. Most acids are always aqueous. That makes them an acid. It produces hydrogen chloride gas, that's HCl gas, and aqueous sodium sulfate. So that's sodium sulfate, aqueous. So here, we really want to look at this sulfate on both sides. We have 1 balancing each one, so we're pretty good there. But we have 2 of the hydrogens that are attached to that one, and only 1 of the hydrogens there. So we need to do something to help balance that a little bit. So one thing we could do is throw a 2 in front of this guy. If we throw a 2 in front of there, that gives us those 2 hydrogens. Now we're balanced with the hydrogen. Looking at chlorine now, we have just 1 chlorine on the left, but now we have 2 on the right. So we need to put a 2 out in front of there, and that 2 then offsets and makes us have to balance the sodium as well. Oh, I'm sorry, this should be, that's where I was messed up. That should be Na2, so sodium sulfate, the sulfate SO4 is a 2 minus, so it needs 2 plus 1 sodiums to balance it. So we're balanced at that point then. We have 2 of that sodiums there, and we have 2 sodiums there. 1 sulfate, 1 sulfate. We have 2 hydrogens, 2 hydrogens, 1 chlorine, 1 chlorine. Everyone's happy. D, let's read it. Aqueous solutions of phosphoric acid and potassium hydroxide react to produce aqueous potassium dihydrogen phosphate and liquid water. So aqueous solutions of phosphoric acid, which is H3PO4, aqueous, and potassium hydroxide, that's KOH, react to produce potassium dihydrogen phosphate and liquid water. So this is aqueous, H2O liquid. So again, starting with the more complicated one, we have a phosphate, that PO4. I like to deal with the ionic compounds all as one because they're usually not going to break apart, and if they do, we can look at them individually. But usually, if we have a phosphate on one side and a phosphate on the other side, similar things are going to happen to them. So we have a 1-to-1 ratio there. We also have this stray oxygen that we need to worry about as well, but they're balanced with that water on the other side as well. The hydrogens, that H2 here and then H2 there, makes 4 hydrogens on the product side, and then H3 there and the H there makes 4 hydrogens on the reaction side. So that's balanced already. Looking at potassium, K, there's 1 K on either side. That's already balanced. I would say this is already balanced. As is. There's the stoichiometric coefficient for each of those compounds is just going to be a 1, basically. Moving on to the next one. For these, from the balanced molecular equations, we want to write the complete ionic and net ionic equations for the following. So basically, all of these compounds, we want to break up those ions and write them kind of as all of the individual ions themselves. And then we want to find any spectator ions that might be floating around, anything that's the same in the product and the reactant side. And then we can cancel those out and then rewrite that equation in its more simplified net ionic form. So doing that, what I'm going to do is I'm going to write these first just as their net ionic compounds, breaking apart those ions, and then we can go from there. So the first one has 2K plus aqueous. All of these are going to be aqueous if they're ionic, because for them to really break apart, they need to be soluble in solution, usually in water. So plus, I'm going to say C2O4 would be a -2 plus Ba plus 2 plus OH. That's 2OH, and I forgot all my aquei. Is that the right plural for aqueous? I don't know. But let's put them in there. Kind of packing these in. I always do that when I forget my aqueous. I kind of pack it a little too close. All right. So that's the reactions, or the reactant side. Now the product side has 2K plus aqueous plus OH minus. So 2 of those as well. Aqueous. Since this has the 2 out in front, it applies to both the potassium and the hydroxide. Plus barium 2 plus aqueous. Oh, this is a solid now. So that is really going to be more of a solid. That's going to precipitate out. It's not going to be disassociated at this point. C2O4. I'll say that's a solid. So looking at the common ones, starting with potassium over here on the left, we see that that shows up on both sides of those equations. The same is true for my hydroxides. They're on both sides of that equation as well. What's really left over is C2O4, 2 minus, aqueous plus, Ba, 2 plus, aqueous is producing BaC2O4, solid. So that's the real reaction that's going on there. The rest of it, they're just spectators. They're floating around in solution. They happily stay in solution, and there's no trouble. For part B, we have lead, Pb, and that NO3 is a -1 charge. So the Pb needs to be a 2 plus aqueous, because there's 2 of those nitrate groups, plus NO3 minus, but there's 2 of those. Slide down a little bit, well, just a tad. We're gonna, that's aqueous as well, don't forget that, plus 2H plus aqueous plus SO4 2 minus aqueous is producing that lead sulfate solid, be a lead 2 sulfate at that point, plus 2H plus aqueous plus 2NO3 minus. And that should also be aqueous. It gets tedious writing those down, and I always used to get yelled at by my teacher for not doing it. So, looking at the common ions here, I see hydrogens on both sides. I see nitrates on both sides. Really, our potassium and sulfate is what's forming that solid. So the easy way to do that is you look at what's actually forming a solid in these precipitate reactions, and we're going to then, everything else is going to stay in solution, usually in that case. And you can look at those and make sure that they're the same on both sides. And they have to have that same coefficient as well. So if you lose one of the hydrogens in that case, or if you lose one of these phosphate groups to a solid, then part of it doesn't stay. Just what's remaining is left as a spectator. So writing that down, that's, keep it blue, Pb2 plus aqueous plus SO4 2 minus aqueous is going to produce PbSO4 solid. And that's our net ionic reaction for that one. Part C, let's go up. Last one. This one's a fun one. I'll tell you why. So calcium carbonate plus H2SO4 aqueous is going to produce, and here I'm writing the whole thing down again just so I can have it a little bit lower. CaSO4 solid plus CO2 gas plus H2O liquid. So on this equation, you would think that this should easily dissociate and produce this guy when it goes down. But to do these precipitation equations, one thing we have to look at is our solubility tables, and to find out which compounds are soluble, with what other things, which ones are insoluble, and they actually precipitate out of solution. So let me switch over here. So this is the table in your textbook here, and you see these ions right here, usually the positive, sometimes the negative ions. If they contain those, they're going to be soluble in this case, with a few exceptions. And they have some exceptions there. One of them, SO4, is one of the ones we're dealing with here on the product side. And when that is around calcium, it's not soluble. So we're getting that in our product. We see here, that's what we have going on over here. So that's good. It's precipitating out of solution. But one thing that would concern me a little bit, if I scroll down a little bit on there, the insoluble compounds here, you see carbonate here. Carbonate is insoluble with compounds with with the exception of group 1 cations or ammonium. Well, calcium is group 2 cation, not a group 1. So this should be insoluble as well. Going back here, this guy should also be insoluble. It should stay a solid. Now, all of these solubility things, it's really what we call a equilibrium, where it's constantly moving back and forth between a solid and a dissociation and then back again. It really strongly wants to be a solid in this case, but some of it is going to disassociate. And when that tiny bit of it does disassociate, it becomes this calcium 2 plus aqueous plus CO3 aqueous. This would be a -2 or 2 minus, plus our hydrogens, they're going to dissociate. Oops, 2 up front, plus aqueous, plus our sulfate. That's pretty happy next to hydrogen. It wants to be a -2 as much as possible. It's going to react. Now, it does produce this calcium sulfate as a solid. And just like with the calcium carbonate, it's kind of going in that equilibrium state back and forth really quickly. But the key to this reaction is this CO2 gas. Plus, and then I'll add H2O just to be complete here. So that CO2 gas is produced from this CO3, this carbonate here. Basically, when that hits these hydrogen, this acidic water, basically, these hydrogen ions, they steal one of the high oxygens from it, creates that CO2 gas. That CO2 gas, since it's a gas, bubbles out of the solution and escapes the solution. So the reason why it doesn't reform back into a solid is this gas here is leaving. It leaves the reaction. And when we remove our product during the reaction process, it drives this reaction to the product side. It's making this, even though only tiny bits of it become soluble, as it becomes soluble in water, it goes away. Because it creates that CO2 gas, that gas escapes, it can't reform into a solid, and then as more becomes soluble and disassociates, more of it goes away as gas. So that is a really fun reaction. Now, if we wanted to write that net ionic reaction for it, in this case, there's no real spectators going on here. We have a solid that's produced, we have a liquid that's produced, and we have a gas that's produced. We have nothing aqueous left in there at the product side. So I would even say this one is the net ionic reaction for this right here, just by pulling apart that solid on the product side over here. That's the final answer I would put on there. It's just a really cool reaction because this idea of by removing one of the products, it drives that reaction to completion, even though it's very reactant favored to begin with. It's called the Chatelier's principle. So you're going to see that a lot in chemistry as you go farther in chemistry. The next equation here is number 19. We're going to classify the following as acid-base reactions or oxidation reduction reactions. So acid-base reactions, it's really one of the two compounds between the reactants and the products. It's gaining a hydrogen ion, or it's losing a hydrogen ion. There's a transference of that proton going back and forth, essentially. And for the oxidation reduction reactions, you're really looking at whether or not you have this change in charge going on the atomic level. So if one of the atoms in there is changing from a neutral to an ionic charge, or neutral to a plus or neutral to a minus, we have that oxidation happening, or oxidation or reduction. So oxidation, how I remember which is which, oxidation, it means it loses electrons. And this can be apparent if it starts out as neutral and becomes positive, which means it's losing a negative charge, which makes it more positive after the reaction happens. That's an oxidation. A reduction is kind of the opposite. The reduction means then it's gaining electrons. So it becomes more negative or less positive, either way. So that's the definition of oxidation and reduction for these. So looking at these equations, really how I would approach this is just looking at the charge, the ionic charge from different things. So if I were to just start writing out the ionic charges for part A, I'd have sulfur, which is a -2, and sodium, which is a +1. +1, but there's 2 sodiums, balances that, so it's a neutral charge. Looking at the right-hand side, I have a +1 on my sodium and a -1 on my chloride. There's 2 of them total, so we do have a balanced reaction, and there's no change in charge between the sodium. Looking at the hydrogen chloride here, chloride's still negative, hydrogen's still positive. We got a balance there. The chlorides stays a negative charge on both of those. Looking at the second side, we've already dealt with the NaCl2. This is still going to be a 2-, and we have a +1 on the hydrogen. But all that's really happened is our hydrogens have moved from it being attached to the chlorides to being attached to the sulfurs, which makes this an acid base. On the next equation, we have sodium solid. We have a solid sodium, which is a neutral charge. Oh, the left. And it is bonding to chloride on the right. So that's going to actually be a positive charge from a neutral charge. Put a little N up there for neutral. Okay, put a 0 maybe. This is 0 charge to it. So you see how the sodium is changing charges. It's actually losing an electron. It's going under an oxidation. So this is what would be oxidation reduction. We call it a redox reaction. For part C, magnesium again starts at a neutral charge, and it moves to be +2. Magnesium ionizes at +2. And it does that because it's a redox reaction. Oxidation reduction. It's going under oxidation. So anytime you get that change in charge, you can tell that it's an oxidation or reduction. If it's becoming more positive, going to be an oxidation. If it's going to become less positive, more negative, it's going to be a reduction. For part D, we got magnesium 2 plus, oxygen's 2 minus. So that's pretty happy. Jumping over to the product side, we still have a 2 plus. Chloride is, they're 1 minus, but there's 2 of them. Just put 1 negative there. So the magnesium has not changed charge. The oxygen is 2 minus. Jumping over to the right hand side, we have a 2 minus here, and we have a plus 1 for the hydrogen. So there's no change in charge with the oxygen. Jumping back, we have a plus and a minus for the hydrogen chloride. There's no change in charge. Just the hydrogens are moving around. The hydrogen moved from being attached to the chloride to being attached to the oxygen. Magnesium then bonded to that chloride, and we have an acid base. Because acid and base is really just the moving of a hydrogen ion. That proton jumps from one thing to another, disassociates it into water, and then bonds to kind of a strong nucleophile. For part E, we have potassium, which is 3. We have, potassium. Then we have phosphorus, which is then a 3 minus. Going on the right-hand side here, we have a potassium, which is still a plus. But now this PO4 as a whole, we can think of, this is a 3 minus. This oxygen started out as a neutral thing. So, but since the oxygens all bonded onto that potassium, I would say this is a redox. Because one of these oxygens is, for them to be bonded together, one of them is more positive, one of them is more negative. It's really a really balanced thing. They're the same atom, so the electronegativity is the same. It's pulling equal bonds in both directions. But when this PO4 happens, we have that phosphorus bonded to 4 different oxygens. I think there's some double bonds in there of sorts. I forget. But the idea is they're pulling that electron negativity away from the phosphorus itself, and they're changing the charges of everything. So it would be a redox reaction. Plus, there's no hydrogens transferring between the 2 different atoms or compounds. For part F, the last one here, we have potassium, which is positive. Hydroxide as a whole, OH, is negative. We have hydrogen, which is positive. We have that phosphate, which is a 3 minus. Again, on the right-hand side, we have a potassium, which is positive. That matches. We have that phosphate, which is going to be a 3 minus. Okay, and that balances with that, and it balances, it's the same charge as that. So there's no real redox happening there. What's really happening is we have hydrogen bonded to hydroxide to make water. And that is basically the most basic, pardon the pun, acid-base reaction. When you have hydrogen ions bonding to hydroxide ions, that's kind of creating water. That's the most basic, the most simplest form of an acid-base reaction. I'm going to jump ahead here. And in these ones here, we're going to talk about the percent yield that you get out of these things. This is number 52 out of there. Here we have automotive airbags, which inflate when a sample of sodium azide, which is NaN3, is a very rapidly decompressed. So in this reaction, they have the equation written here. We have this sodium azide, which decompresses into sodium solid and nitrogen gas. That nitrogen gas rapidly expands, and it does it so quickly, if you get into an accident, it pops open before your face is able to plant into it. But what's happening is we want to know what mass of sodium azide is necessary to produce, they say 2.6 cubic feet. We like liters, metric system's better. So we're going to look at the 73.6 liters of nitrogen gas. And they tell us the density of that gas. And we want to know then what mass of the sodium azide is necessary for this. I'm sorry, this isn't a percent yield. It's just kind of like qualitative analysis of things. So in this case, we have that reaction here, and we can figure out how much we need of the reactant to make that product on the end. And we want to make sure we have enough nitrogen gas to fill that airbag. If we have too much, it pops. And if we don't have enough, it's not soft enough. It's not enough inflated enough to stop it. So to do that, we use basically a dimensional analysis, and we're going to go through kind of this reaction line that I like to use. So draw my line here. And it's a lot of dimensional analysis, breaking down from what we have to what we need at the other end and doing all the unit conversions along the way. So we're starting out with 73.6 liters of nitrogen gas. Well, that's how much we want to produce, right? But since we're going to work our way backwards to the reactant side, we're going to start out on the left side of my line, 73.6 liters. Draw that line. I'll say that's liters of N2, actually. And we need to change that liters into mass. And it tells us the density, so we can use that density. Again, following just the units there, if we multiply these two together, we get grams, right? Because we have liters times density gives us the mass of the object. So let's multiply 1.25 grams per every liter. So at this point here, oops, that should be in purple. I have grams of N2. The next stage is we want to convert it into moles, because when we're dealing with two different types of compounds, that center channel that we can transfer and convert everything through is through that molar ratio and the balanced equation that we have up above. So that molar ratio, to get from grams to moles, we have to use the molar mass. And the molar mass of N2, the molar mass is grams per mole, and we want to divide by that. So to find that, we have to do 2 times the molar mass of nitrogen, because it's dinitrogen, right? Which is 14.007. That's going to be in grams per mole. So at this point, this is if we're doing that math across there, we're going to end up with moles of N2. So the next step is that stoichiometric ratio. That ratio of how many moles of N2 is produced for every mole of NaN3 that we start out with. So on the top, we have moles of N2. So I need to write how many moles of N2 on the bottom, and my moles of NaN3 on the top. And looking at our ratios in our equation, because that's where we pull those numbers from, we have 3 moles of N2 for every 2 moles of NaN3. And watch our units when we do our dimensional analysis. The liters are going to cancel out there, giving us grams at this point. The grams cancel out there, giving us moles at this point. The mole is going to cancel out there, and so is the N2. We're left with the moles of NaN3 at this point. But we don't want moles directly. We want to find out what mass is necessary. So we have to turn moles into mass. We have to use that molar mass of NaN3 this time. And instead of dividing by it, because now we have moles on the top instead of grams, we need to multiply. So multiplying, if we look up, sodium is 22, I want orange, 22.99 grams per mole, plus 3 times our nitrogen. And you just look those up on your periodic table. It should have the average molar mass there, and use that. We have to sum together all the molar mass of each atom within the compound to get the molar mass of everything. And it's per mole. So unit-wise, the moles cancel. We're left with grams. So at this point here, we had moles of NaN3, and over here, we're left with grams of NaN3. And that's what they're asking for. What is that mass of sodium azide? So now we can just do the math. And when we do the math, basically, if it's on the top of this line, we're multiplying. If it's on the bottom of that line, we're dividing. That's how I work it through. So pulling up my calculator, trusty calculator, 73.6 times 1.25 divided by, throw a parentheses in there, 2 times 14.007. And then I'm going to multiply by 2, divide by 3. I'm going to multiply by 22.99 plus 3 times, slide this over, 14.007, close my brackets. There we go. And that matches what I had. Yeah, good. 142.3. So sig figs, gotta look at sig figs. We have 3 sig figs there. That's one of the numbers they gave us. This is 3 sig figs as well. This is a conversion ratio. That's a stoichiometric ratio. This is a conversion ratio. We're not using those to calculate our sig figs. We're left with 142 grams of NaN3. So that's how we do that with these lines. It keeps it real simple, and it saves you from having to round intermediately and get an error at the end. This way you can write it all down. This is the steps I'm going to do for it, and then you just do the math straight across. And we're going to be doing that a few times today. The next problem, they want to know what volume of 0.750 molar hydrochloric acid solution can be prepared from the HCl produced by the reaction of 25 grams of NaCl with excess sulfuric acid. And that's a lot to say. So really, what's happening is there's this reaction here. And this reaction is producing hydrochloric gas, HCl. And that HCl can be mixed in with water, and when it does, it disassociates with hydrogen plus and Cl minus, and it creates this acidic water, basically, this hydrochloric acid solution. And we want that hydrochloric acid solution to be 0.75 molar. So we kind of skipped molarity last week, so I'll talk about it a little bit here. When we talk about molarity, what we're really talking about is the moles per liter. So it's how many moles of something we have divided by the volume of the solution that it's in. So if we had 1 liter of something and we mixed in, say, 500 moles, or like 0.5 moles even is probably a better way, 0.5 moles into a liter of water, we would have a molarity of 0.5 because we had 1 liter of water. Now, if we mixed in 0.5 moles into a half a liter of water, well, then we'd have that 0.5 divided by 0.5, we'd have 1, so we'd end up with a molarity of 1 molar. So that's just kind of a rough estimate. So what we really need to do is determine here how many moles of HCl that we have, because for every mole of HCl, you get this hydrochloric acid solution. And they're not giving us a volume per se. They're just saying, what volume do we need? That's what we're trying to find. What volume do we need to have based on the moles that are created with this much NaCl? So let's run through that a little bit. So we start off, again, my reaction line. We start off with 25.0 grams NaCl. And we need to convert that now to moles. It's always a good first step. Get it into moles. That's really what we're trying to do with a lot of this stuff, is to get it into moles, then use that molar-molar ratio to get it into something else. So here, to do that, we need to divide by its molar mass. Okay, so sodium, like we said earlier, 22.99, plus chloride, when I looked it up, was 35.453. Those are grams per mole. So now we have to multiply by that molar-molar ratio. So here we started out, we had grams of NaCl. At this point, we're left with moles of NaCl. We want to find how many moles of HCl. So we need to go through that molar-molar ratio. So for every mole of NaCl, how many moles of HCl do we have? So looking at our equation, we look at the coefficients in front of there, and there's nothing there. So it's really a 1-to-1 ratio. Having a 1-to-1 ratio there leaves us at this point with moles of HCl. So let's do the math on that now. 25.0 divided by parenthesis 22.99 plus 35.453 close parenthesis, and we can multiply by 1, divide by 1. Don't really need to do those last two. It's just gonna keep it the same. So we end up with here it's a little different than I got before. 25 grams. Looks like I did it right. I didn't do it right. That's a multiplication. Should be a plus. Because we're adding the molar masses together and then dividing by that. So let's do that correctly. Hey, that's what I got before. That's 0.428. I'm running to 3 sig figs because the one number I used in there was 3 sig figs. And this is moles of HCl. But we're not done yet. We want to know what's the volume that's needed to get this molarity. Well, that molarity is, again, moles per liter. That's the units that's in. And we have moles here. So to get a volume by that, we can see if I were to switch to a nice green. Let's do a darker green. That moles per liter, I want to, I wrote it the wrong way. Start off with moles. I want to divide by mole per liter. So the moles cancel out and I get liters. So just by following the units there, I can tell what I need to do on the next step. So that means I need to divide the moles of HCl by that molarity, that 0.750 mole per liter. And the moles and moles we cancel out, and we have liters in the denominator of the denominator, which means it pops up to the numerator. And we can get 0.428. To not have a rounding problem, I'm going to grab that number there. I'm then going to divide that whole thing by 0.75. And that's what I get. This equals 0.570, 3 sig figs, times, nope, I don't need the times 10, just liters. So it's a little over half a liter, almost 0.6 liters. And that is the volume that we need to mix in. So if you did this reaction, collected all the HCl, put it into that much water, you would have a hydrochloric acid solution that is 0.75 molar. This next one, a sample of 53 grams of carbon dioxide, is obtained by heating 1.31 grams of calcium carbonate. What is the percent yield for this reaction? So here, they're telling us the sample of carbon dioxide. They're telling us how much calcium carbonate we're starting it with. So this is kind of the obtained yield. That's how much we got out of it when we did it. This is how much we start with for calcium carbonate, the starting mass. And we want to know that percent yield. So percent yield is equal to the obtained yield. How much product were you able to obtain and gather, dry, weigh, after you dry it and everything, divided by the theoretical yield. The theoretical yield is like if everything was perfect. So if you did everything right, you didn't lose any to any possible loss mechanism. Basically, what the balanced chemical equation and the stoichiometry tells you should get out of it, you get every possible bit of it out. Everything reacts. That's your theoretical yield. That's what we're going to calculate. And we're going to compare that then through this equation to our obtained yield. If we multiply it by 100, we get it to a percentage, is all. So looking at this guy, we again are going to do our reaction line. And we're going to start off with this 1.31 grams of calcium carbonate. So that's 1.31 grams of CaCO3. And we want to convert that then into moles. And again, to do that, we have to use its molecular mass. So the molecular mass, you can also just look this up on the internet, but it's good to know how to go about doing it. So if we look up calcium, we get 40.078. If we look up carbon, you get 12.011. And we're going to add that to 3 times oxygen, which is 15.999. Some of these you just start to know if you do this enough. Grams per mole. Like I've got carbon, oxygen, nitrogen, some of those common ones, hydrogen, memorized pretty well. Anything outside of that, I usually just look it up to make sure I'm remembering things correctly. So then we have to multiply by that stoichiometric ratio. For every, let me mark where I'm at first. At this point here, we start out with that grams of CaCO3. After we do this, we have moles of CaCO3. So we're just converting it into moles. And then we do that molar-molar ratio. So we need to find moles of CO2, because that's what they're producing here, and moles of CaCO3. So we need to figure out what is that ratio between those two things. And we can look at their equation to do that, finding the coefficients in our equation for those two compounds, which again is going to be 1 to 1. Last thing we have to do is convert that moles into grams, because we need to compare it to the grams that we have. And we can't do this yield. They need to be in the same units to do that. So we need to convert to grams. To do that, now we have moles. We want to turn it into grams. So since we have grams and we want to turn it in, we have moles. Oops. We have moles. We want to turn it into grams. We need to multiply grams per mole, which is your molar mass. So the moles cancel and we get grams. So let's do that. The molar mass of CO2, because that's where I'm at right now, I have grams divided by grams. I have moles of calcium carbonate. We have moles of CO2, so we need to multiply by, this is going to be moles, divide by moles and multiply by 12.011 plus 2 times 15.999 grams. Unit-wise, the moles cancel and we're left with grams. So let's run that through our calculator. Clear it here. 1.31 divided by, parentheses, 40.078 plus 12.011 plus 3 times 15.999. Close my parentheses. I can multiply by 1, but don't really need to. Might as well. 1 divided by 1, just to do this column here. And then we're going to multiply, do my parentheses again, by 12.011 plus 2 times 15.999. Close my parentheses. So your parentheses are important when you're doing these. That's why I write them down. If you found this value on the internet, it would be all together already. And we can press enter. That, again, doesn't match what I had before, because, I don't know. 3 plus, maybe I did it wrong this last time. Grams. pretty close though. So I probably did it wrong before. I'm getting 0.576 grams. Right? Just double, triple checking it to make sure I'm doing it right. I'm adding, just add my parentheses, multiply and divide. Yep, that's all right. Okay. And it makes sense too, still compared to what we have, because our obtained yield should always be less than our theoretical yield. You can't make something out of nothing, right? So now to find our percent yield, that's going to equal how much we obtained, that 0.53 grams, 0.53 grams divided by this 0.576 grams. This is really at the end of everything. That's how much we got. We're going to multiply then by 100%. So we say 0.53 divided by that figure times 100. And we're getting a yield of 92%. Rounded to 2 sig figs because we got 2 sig figs there. So that's how we can find our percent yield in things. And it all comes down to doing that reaction line and following the dimensional analysis to transform what we have, the information we have, into what we were looking for. Okay. This problem here says outline the steps needed to solve the following problem, then do the calculations. So we have ether, which is C2H52O, which is originally used as an anesthetic, but it was replaced by a safer, more effective medications. It is prepared by the reaction of ethanol with sulfuric acid. And they give the chemical equation here. They want to know what percent yield of ether, what is the percent yield of ether if 1.17 liters, and they give us the density, is isolated from the reaction of 1.5 liters of C2H5OH. So they want us to know what steps are you going to use to solve this problem, and then they want us to go through and solve that. So I'm going to write down the steps. And really, the first thing I'm doing here is I'm finding the theoretical yield. So step 1, I want to convert the C2H5OH, that ethanol, into grams. And I'm going to do that because I'm converting a volume. The volume of ethanol into grams. And I do that by taking that volume and I multiply by the density. Because density is grams per liter and volume is going to be in liters, so those liters cancel out and we're left with grams. I can write that. So that's liters times grams per liter equals grams. Step 2 is to convert the mass, that mass that we just found of ethanol, into moles. So to do that, of course, we have to use that molar mass. So that's the mass divided by the molar mass, which gives us the moles. I can write that here, so it's like saying grams divided by grams per mole. Let's write that better. Grams divided by grams per mole is going to equal moles. I don't have room to write that. I'm really a big fan of kind of following the units when you do these types of things. And don't forget your units while you're doing your math. if you write a long equation, the first thing you can do before you crunch any of those numbers is kind of doing that dimensional analysis, making sure you get the right units at the end of the day. And then you can crunch all the numbers, because if you screwed up somewhere on the units, the number's not going to be right either, most likely. So the next step is to convert that moles and that's still ethanol, into moles. Oops. Moles doesn't have a T, of ether. And we do that through that mole to mole ratio, that stoichiometric ratio that's so important to chemistry. Mole to mole ratio. And that's really good because it's multiplying by moles over moles, so the moles cancel the moles out actually, and we're just left with this number, this conversion factor between moles of this substance to moles of that substance. The fourth step is to convert those moles of ether into a mass. And we can do that by using, again, the molar mass. In this case, instead of dividing it like we did before to convert mass into moles, we're going to multiply those two together to get moles into mass. So that's going to be my moles times my molar mass. Or I can write it as mole times grams per mole equals grams. Because what we want there is grams in for our mass. The next step, step 5, is to convert that mass into a volume. The mass of ether into a volume. And to do that, we need to use the density. And they nicely gave us the density that we're going to be using for, that's the ethanol density. The ether density is this one here. So density is grams per liter. So once we have that mass, we can multiply it. That's mass, or not multiply, we divide by density. Unit-wise, that's grams divided by grams per liter, which equals liters. And once we get that liter, we now can figure out that percent yield, because that would tell us the theoretical yield that we have. So the last thing is to find percent yield. And that is by using the obtained yield divided by the theoretical. And we multiply by 100 to get a percent. Ether, which is this guy up here, that's going to be 0.7134. 0.7134. That's going to be grams per liter. Is that in milliliters too? That is in milliliters too. So let's put 10 to the negative 3, because liters times 10 to the negative 3 becomes milliliters. So I'm just putting those unit conversions in there. Now we can solve it. Plugging into our calculator. Yeah. That's 1.5 times 0.7894. I'm going to divide by, I like to put my 10 to the power of negative 3 in parentheses. And then I'm going to divide again by 2 times 12.011 plus 6 times 1.008 plus 15.999. Close my parentheses. So I can multiply by 1, which doesn't really do anything, but dividing by 2 now becomes really important, right? And that's that stoichiometric ratio, that multimole ratio that we have. Sliding back over this way now, I'm going to multiply by parentheses. Here, I'm down here now. 4 times 12.011 plus 10 hydrogens plus an oxygen. Then we can multiply by 10 to the power of -3, dividing by that 0.714 grams. And we get 1.33. So just looking at my dimensional analysis, I forgot to do this earlier. Liters cancel out there. Grams cancel out there. My moles of ethanol go away there. My moles go away here. My grams go away there. I'm left with liters of ether. So this should be liters of C2H5 2O. So that's how making sure those units match lets me know that if I did all the math correctly, then I should have 1.33, and this should be in liters. So how does that compare? Let's do our percent yield. We see that 1.17 liters was obtained of ether. So to do that, that's 1.17 divided by 1.33. Both of those are in liters, which cancel. And then we multiply times 100%. That gives us our percent yield, 1.17 times 1.33 times 100 is equal to 100. I did a multiplication there. Whoopsie. Let's grab that again. I should not have multiplied. I should divide because I got a value much larger than 100%. Now that's better. That's 87.9. We want 3 sig figs. We actually, 87.9 rounds up to 88%. And that's our yield. We want 3 sig figs, so I should really do 88.0. 0.0%. Again, this value up here was really to 4 sig figs, that 1.500, but this value was 3 sig figs. So this one on the bottom should really be brought out to 4 sig figs, but ultimately I'm pulling it from, I should be pulling it from my calculator. I didn't. Let's redo that. Divided by that number times 100. Oh, look how much it changes things. So just by pulling it from the calculator instead of, and not having that rounding error, I'm really at 88, or I want 3 sig figs, 87.7%, which is really close to 88, but it's not quite. So that is my percent yield for this guy. And we are all out of time now, so I'm going to leave it right there. Again, if you're having any trouble or struggling with the fast pace of this problem, definitely reach out to us through Penji and schedule a tutoring appointment with Amir, or stop in on Saturday and a drop-in tutoring that I have following my Saturday live stream. Saturday live stream is at 2 p.m. and then it usually goes on for an hour, maybe a little bit more, and then I jump into the drop-in rooms and I'm there until 5 o'clock. Or you definitely also check out the YouTube channel that we have. That YouTube channel, again, I'll paste a link to it here. That has all the past videos. This one's going to be up there by the end of the day, hopefully. Just a great way to review all the old stuff we've covered and make sure you're on top of stuff. Have a great week and enjoy yourself.